channel Knowledge of. Friends, subscribe to our channel and click the bell icon for the latest update. Today we're gonna start with your chemistry for class 12, that will be in your class 28. Before 28 classes we had completed your 27th classes, where we had completed your unit 1, unit 2, unit 3, unit 4, unit 5, unit 6, unit 7 and unit 8 we had completed. In the last classes we had started with unit 9, which is your coordination compound, that what we have to talk about it, and that is a window which is important as well. Before starting with the sessions, it's a huge request from my side to all the viewers to please go through with the subscribe button and please like, share and subscribe my channel, so that many and maximum people get information about it, and that you can also go ahead for the same, which is on the same cases we had started with the isomerism in the coordination compound, where we had started with the geometric isomerism. In geometric isomerism we had even though done about the geometric isomerism, isomers, cis and trans of that, and now we'll go ahead for the geometric isomers, cis and trans for COCl2. We'll go ahead for the same. Geometrical isomers, cis and trans of COCl2En twice, that we have to talk about it. And in this type of isomerism also arises when a didentate and ligands L and L. Example is your NH2 CH2 and CH2 NH2 En, that are present in the complexes of formula, which is MX3L bond L twice, that we have. On the same cases we have a figure for the same, that is being represented here is En, CO, this is Cl, Cl, En, this is En. So this has been for the same case. We can say that here is your En, then it will be the shifting of Cl, we had shifted that only. This is being a here En, it will be En here as well. Then one Cl is here, one Cl is here. Okay, this is for the COCl2En2 that we have, that has been represented here. The same cases here for the another type of geometrical isomerism that occurs in octahedral coordination entities of the type that Ma3B3, like CONH3 whole thrice, NO2 whole thrice, if three donor atoms of the same ligands occupy the adjacent position, that adjacent positions that we have here, and the adjacent positions of the corners of the octahedral face, we have the facial isomers, that is FAC, and with the same case when the positions are around the meridian of the octahedron, that we get the meridional more isomers as well. On the same behalf of it, we go ahead for the structure for the same, and that is being representing here NH3 CO, this has been NH3, being NH3, this is NO2, which is also NO2, being NO2. Okay, so it will be like, was like this. Okay, this is your FAC, and the another we have for the same is CO bond NO2 bond NO2 bond NH3 bond NO2 bond NH3 NH3 as well. This has been the more here, that is we have. So this is the facial and meridional, which is Mars isomers, and that is CO NH3 whole thrice, NO2 whole thrice as well, that has been representing here. We'll go ahead for the another one, that has been the important question for the same. With the same cases we go ahead for the same, and that what we have to discuss here in the detail. The question is being asked is, why is geometrical isomerism not possible in tetrahedral complexes having two different types of unidentate ligands coordinated with the central metal ions? That has been important, and that for the same we will talk about the solution for here. We'll go ahead for the same for the question first. So the question is, why is geometrical isomerism not possible in tetrahedral complexes having two different types of unidentate ligands coordinated with the central metal ions that we have. For the same, the solution for the same we have there, the tetrahedral complexes do not show geometrical isomerism because the relative positions of the unidentate ligands attached to the central metal atom that are the same with respect to each other here. That has been the answer here. You can just go ahead for the same, and I just make you write here as well, so that many of the students are making notes. So for the same we have for them, I just write it down. Tetrahedral complexes do not show geometrical isomerism because the relative positions of the unidentate ligands attached to the central metal atom are the same with respect to each other. That we have to talk about it. Now we'll go ahead for the same, and that has been the another one is your optical isomerism. That is the second part of your stoichiometrics, and first is your geometrical isomerism and the second is your optical isomerism here. So in terms of optical isomerism here, that what we have to talk about it. In this, the optical isomers are mirror image that can be superimposed one on one another. These are called as your enantiomers, and the molecules or ion that cannot be superimposed are called a chiral. That the two forms are called a dextro and a lubo. That depending upon the directions they rotate the plane of polarized light in the polarimeter, where D rotates to the right and L is to the left here, where optical isomerism is common in octahedral complexes that involving didentate ligands here. In the same cases for that what we are representing here, this is AN, this is your EN and EN. Okay, this is 3 plus, this is mirror, CO, EN, 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 or those are the same here as well, that has been representing. So here for this we have as your 3 plus as well, that has been representing. So on the same cases, this has been your live over here. Okay, so this is an optical isomers. They are D and your that is your D and L of COEN 3 plus, that has been representing. So that for the optical we go ahead and I just write it down for you all. Is optical isomers D, that is your, this is your dextro and levo of CO EN thrice 3 plus. Okay, that we have. So in optical isomerism, that optical isomers are the mirror image that cannot be superimposed on one another. These are as your enantiomers. The molecules or ions that cannot be superimposed are coilterals, and the two forms are that called dextro and levo. Depending upon the directions they rotate the plane of polarized light in a polarimeter, their D rotates to the right and L rotates to the left. Optical isomers is common to in octahedral complexes involving the didentate ligands here. We'll talk about the another one, that is the in the coordination entity of the type, which is PTCl2En twice 3 plus 2 plus, that only the cis isomers shows optical activity here. So for the same we will be finding it out for here. That has been representing here is En, PT, Cl, Cl 2 plus. This is En as well. This is your dextro mirror, Cl, Cl, PT, En, En. This is LIVO in 2 plus here that we have. This is an optical isomers D and L of cis, and which is we have for the figure which has been represented for PT Cl2 En 2 2 plus, that we have for the same, and that we have to go ahead for here. Now we'll go ahead for the another question here, that what we have to discuss as well. This has been the question. You have to draw the structures of geometrical isomers of FeNH3 whole twice and CN4 as well, that has to be representing, and that what we have to draw here. The another question we have for the respect towards it is your, the another is your out of the following two coordination entity which is the child optically active, that what we have to find out. So we'll do that, but before starting with this we'll do these questions as well, and then we'll complete it the another activity here. The question is, you will have to do the first one, that is your draw structures of geometrical isomers of FeNH3 whole twice Cn whole 4 minus. For this we have to need a solution here, and for the same we'll go ahead. This has been Cn, this is NH3, NH3, Cn, Cn, this has been Cn, this is your Fe, cis. Next is your Fe, this is for Cn, minus Cn, here it is NH3, Cn, Cn, NH3, Cn, that we have. This is for trans. Okay, now we'll go ahead for the another question that we have to talk about it. It is the another important questions here. As the question, out of the following two coordination entity, which is chiral, this has been optically active here, what we have to find out. Let's go ahead for the same. Out of the following two coordination entities, which is chiral, or you can say that optically active. Okay, that what we have to find out. So for the first one, it is cis CrCl2 OX2 3 minus. For this we have to find out. So first we'll go ahead for the same for this. The another we have here, second one, just we'll do it here only. That has been the trans CrCl2OX twice 3 minus. This is cis and this is trans. That's what we have to talk about it. So we'll go ahead for the same. That is for the cis we'll do first. OX. This is Cr, Cl, Cl, and this is OX. So this is cis CrCl2 OX power 3 minus here, and this is for trans. We have to go ahead. It's your Cr, Cl, Cl, OX, OX 3 minus that we have here. This has been also 3 minus that we have represented here. So out of two, here cis CrCl2OX twice 3 minus is the chiral optimal active here. This has been the chiral, or you can say that optically active. That is where we have to answer it out. We'll go ahead with another one that we have to discuss here, which is the another one, the third property we'll talk about with the isomerism, that is your linkage isomerism. So let's go ahead for the same here. So the third we'll talk about it, that is linkage isomerism. In terms of linkage isomerism, the linkage isomerism arises in the coordination compound that containing the ambidentate ligands, and a simple example is provided by the complexes containing the that is your thiocyanate ligands such as NCS, which may bind through the nitrogen to give NCS or through sulfur to give MsCN, where Jurgensen discovered such behavior in the complexes of CONH3 whole twice whole of 5 NO2 and Cl2, which is obtained as a red form, and in which the nitrite ligand is bound through oxygen, which is ONO, and as the yellow form, that in which the nitrite ligand is bound through nitrogen, which is NO2 here. We'll talk about the fourth one, that has been the coordination isomerism. Coordination isomerism, where this type of an isomerism arises from the interchange of ligands between that is your cationic and anionic entities of different metal ions that present in a complex. An example is provided by CONH36 CrCN6, in which that NH3 ligands are bound to CO3 plus and Cn minus ligands to Cr3 plus in its coordination isomers, that CrNH3 whole 6 CONH3 CN6, that the NH3 ligands are bound to Cr3 plus and Cn minus ligands to CO3 plus as well. We'll talk about the fifth one, which is ionization isomerism. That is ionization Isomerism. In ionization isomerism, this form of isomerism arises when the counter ions in the complex salt is itself a potential ligand and can displace a ligands which can they become the counter ion. An example is provided by the ionization isomers, which is CONH3 whole twice SO4Br, and which is your CONH3 whole 5 BrSO4 here. We'll talk about the sixth one, which is your solvate isomerism. In solvate isomerism, this form of an isomerism is known as your hydrate isomerism in case where the water is involved as a solvent. This is similar to the ionization isomerism. Solvate isomers differs by whether or not a solvent molecule is directly bounded to a metal ion or merely present as a free solvent molecule in a crystal lattice. An example is provided by the aqua complex, which is Cr H2O whole 6 Cl3, which is in violet, and it's a solvate isomer, which is Cr H2O whole 5 Cl and Cl3 dot H2O, which is in gray green color here. Now we'll go ahead for the same, that is we have to talk about the another questions here that we have to discuss. That is, indicate the types of isomerism that exhibits by the following complexes and draw the structures for these isomers. So first isomers we have, you have to representing it out as your in the form of K Cr H2O whole twice C2 OC2O4 twice. Second is CO En thrice Cl3 CONH3 5 NO2 NO3 whole twice PDNH3 H2O Cl2 here. So you have to give evidence that CONH3 whole 5 Cl SO4, where CONH3 whole 5 SO4 Cl are ionization isomers, that we have to answer it out. We'll discuss about the bonding and coordination compound here, that has been important as well. That is we have bonding in coordination compounds, that we have to talk about it. So bonding in coordination compound, that has been important here, where Werner's was the first to describe the bonding features in coordination compound, but his theory could not answer basic questions like why only certain element possess the remarkable property of forming coordination compound. Second is why the basic bonds in a coordination compound have directional properties. Third is why coordination compound have characteristics magnetic and optical properties here, where many approaches have been put forth to explain the natures of bonding and coordination compounds. That is your valence bond theory, which is BBT, crystal field theory, which is CFT, ligand field theory LFT, and molecular orbital theory, which is MOT. We shall focus our attentions on elementary treatment of its applications of BBT and CFT to the coordination compound. First, we'll discuss about the valence bond theory here. First is your valence bond theory, which is we had named as VBD. In terms of VBD, according to this theory here, that the metals and or ions that under the influence of ligand that can or use its n-1 d and ns and p ns and p and d orbitals for the hybridization to yield a set of equivalent orbitals of definite geometry, such as octahedral, tetrahedral, square planar, and so on. These hybridized orbitals are allowed to overlap with Ligands orbitals that can donate electron pair for bonding. This is illustrated by the following example that we'll talk about it, and set numbers of orbitals and types of hybridization we talk about here. Number of orbitals and types of hybridization, here we talk about it. In the same cases, we go ahead for the coordination compound. coordination number, we can say that. Type of hybridization and distribution of hybrid orbital in space, that we have to talk about it. So we are talking about the coordination number. We go ahead for the further same. We'll deal with that. So the coordination number we have here is to be as follows. The first coordination we talk about 4, 4, 5, 6 and 6. So here for the 4 we talk about it, that is the S type of hybridization we have is your sp3, and this is your tetrahedral. The fourth we have is your DSP2. This is your square planar. The fifth we have is your SP3D. This is trigonal bipyramidal. Sixth is your SP3D2, which is octahedral. Sixth another we have is D2SP3, which is octahedral. That what we have to talk about it. Now we will be going ahead for the another one which we have to talk about here, is that it is usually possible to predict the geometry of a complex from the knowledge of its magnetic behavior on the basis of the valence bond theory. In the diamagnetic octahedral complexes CONH3 3 plus, the cobalt ion is in +3 oxidation state and has the electronic configuration 3d6, and the hybridization scheme is as shown in the diagram here. That what we have to talk about it. So 6 pairs of electrons, one from each NH3 molecule, that occupy the 6 hybrid orbitals. Thus the complex has octahedral geometry and is a diamagnetic because of the absence of unpaired electron. In the formations of this complex, since the inner of the d orbital, where the 3d is used for hybridization, the complex, which is CONH3 whole twice 3 plus, is called an inner orbital or low spin or spin paired complex here, where the paramagnetic octahedral complexes, which is COF6 3 plus, uses an outer orbital, which is 4d in a hybridization. sp3d2, it is thus called outer orbital or high spin or spin 5d complex. Thus we'll talk about for the orbitals here. So for the same, that for the first one we'll go ahead, and that is being representing here, that is your orbitals of CO3 plus ions. So here it is. Then we have 4s, this is 3d, this is 4s, and this is 4p, that we have to talk about it. Okay, so just arranging it out, we'll arrange it next way. This is D0sp3 hybridized orbital of CO3 plus. So it will be having, and then we have your this is your D2 sp3 hybrid. So this is your T2 only. Next we have your the another one for the same is your CONH3 whole 5, 6 and 3 plus inner orbital or low spin complex. So which is we have here, then we have your one, two, three, four. Okay, so this is your 6 pairs of electron items, oh sorry, from 6 NH3 molecules that we have here. Okay, this is being representing here, and for the same we have representing So with the same cases we have your spin utilization that we will go ahead for the that is your sp3 here, that we have to talk about it. So we'll go ahead for the same, and that is we have here rotation is 1, spin 1, then 1, and then of course we have here that is being 1 only, and this is being representing here itself, that been representing here, and for this is being empty here. This is another one here. It is the rotations for the NPN. This is being the representation here. This is being representing here. Here we have, and this has been representing here only. So this is it is usually possible that what I have shown about it, and that's 6 pairs of electron, then 1 from for each NH3 molecule that occupy the 6 hybrid orbital here, that has been representing and that hybrid orbital, and that's the completely complex has been the octahedral geometry and as a diamagnetic, because of the the absence of unpaired electron in the formations of the complex. And since the inner d orbital 3d is used for hybridization the complex, so CONH3 whole 6 3 plus is an inner orbital or a low spin or a spin paired complexes, where the paramagnetic octahedral complexes COF6 3 minus uses outer orbital 4d in a hybridization, and sp3d2 it is thus called outer orbital or high spin or spin free complex. Thus we'll talk about the orbitals of CO3 plus ions as well. So we'll go ahead for the same. Orbitals of CO3 plus ion. One, two, four. Then we have here, this is your 3D. Then we have 4s, 4p, then 4d. Next is your sp3d2 hybridized orbital of CO3 plus that we have, that is 3D. Here this has been sp3d2 hybrid. This is 4D. Here it is your COF6 thrice, that is we have is your outer orbital or high spin complex. This is being representing here. Which is 3D. So it is being representing here. This is being 4D. And here it is your SP, that is your 6 pairs of electron from 6 F ions here. That what we have. On the same case we have a filling for the same is that we have, and for sp3d2 we have for the same as your, and for CO that we have your that has been representing here. Okay, now we'll go ahead for another one, which is for another one that what we have to discuss about the nickel here, and that is being the orbitals of nickel, then nickel 2 plus, and then the 4 more over that what we have to talk about it. So we'll go ahead for the same. So orbitals of Ni, first we'll do that. Okay, then you have your we have your orbitals of Ni2 plus ion, which is to be as follows. And then it is your, this is one, then you have your another one is your, is being the 2 here. Next we'll talk about for the next one is what we have here for that is being representing as your sp3 hybridized orbital of Ni2 plus, and for that we have to go ahead. This has been your 3D, for S and for P. So for here it will be now we'll go ahead for another one is your NiCl4 twice, that is high spin complex, that is we have and that is your we have. So here 4 pairs of electron from 4Cl minus that we have to talk about it. So on the same case we have a filling here. Then again for another filling we have 4S and 4P for this. It is and we have again another one that has been representing here as well. This is your sp3 hybrid 3D here. Now we have a filling. This has been okay. So in a tetrahedral complexes, 1s and 3p orbitals are hybridized to form 4 equivalent orbital oriented tetrahedrali. This is that L unstated below for NiCl2 3 2 minus, and here nickel is in +2 oxidation state, and the ion has the electronic configuration of 3d8, where the hybridization scheme is also here. And each Cl minus ion donate a pair of electron where the compound of paramagnetic, since it contains 2 unpaired electrons. Similarly, NiCO4 CO that is we have twice that has been in the tetrahedral symmetry but in diamagnetic, since nickel is in 0 oxidation state and contains no unpaired electron. In the square planar complexes, the hybridizations involved in dsp2, and example is NiCN4 that we have 2 minus, and here nickel is in +2 oxidation state and has the electronic configuration of 3d6, where the hybridization scheme is as shown here in a diagram. That what we have to talk about it, and we'll talk about the oxidation orbitals of Ni2 plus ions, that what we have to complete it here only. Let's go ahead for the same, and before completing that, I will just do it here only so that it will be making it helpful for it, and that is even though important for us as well to solve it out. And that has been representing the same here that what we had representing here for the sp2 and the sp2, and then of course the 4p and that NiCN. For the next we'll talk about for the here it is your NiCl4 and here it is NiCN4 2 minus. The other two is the same only, that other two one. So for that I will just it will be a low spin complex. Okay, for that it is your 3D. This is 4. This is your 4 pairs of electron from 4CN group that we have. For the same, it will be this is being representing like this only. It has been representing. So here each of the hybridized orbital receives a pairs of electrons from a cyanide ion, and the compound is a diamagnetic as evident from the absence of unpaired electron. It is important to note that the hybrid orbitals do not actually exist. In fact, hybridization is a mathematical manipulations of wave equation for the atomic orbitals involved. Now we'll discuss about the another one, which is your in terms of magnetic properties of coordination compound. So we'll talk about the another one we have to talk about here is the magnetic properties of coordination compound. So for the same here, the magnetic momentum of coordination compound that can be measured by the magnetic susceptibility experiments, and the result that can also use to obtain information about the structures that adopted by metals complexes. With a critical study of the magnetic data of coordination compound of metals of the first transition metal, this had revealed some complication for metals ions with that to up to 3 electron in the d orbital, like Ti3 plus d1 and V3 plus d2, Cr3 plus d3, and 2 vacant of d orbitals are available for octahedral hybridization with 4s 4p orbitals here. In the same case, the magnetic behavior of these free ions and their coordination entities is similar. When more than 3d electrons are present, the required period of 3d orbitals for octahedral hybridization is not directly available as a consequence of Hund's rule. Thus, for D4 Cr2 plus Mn2 3 plus where D2 Mn2 plus Fe3 plus D6 Fe2 plus Cu3 plus cases of vacant pair of d orbital that results only by pairing of 3d electron, which leads to 1 or and a 0 unpaired electron respectively. The magnetic data agree with a maximum spin pairing in many cases, especially with coordination compound that containing D5 ions. However, with the species that containing D4 and D5 ions, there are complications. MnCn6 for 3 minus has a magnetic momentum of 2 unpaired electron, while MnCl6 3 minus has a paramagnetic momentum of 4 unpaired electrons. FeCN6 3 minus has a magnetic momentum, where that is the 2 vacant d orbitals are available for or octahedral hybridization for 4s and 4p orbitals that we have, and that the magnetic behavior of these free electrons of the coordination entity is similar when more than 3d electrons are present, and the required pair of the 3d orbital of octahedral hybridization is not directly available as a consequence of Hund's rule. Thus, for D4 Cr2 plus Mn3 plus and D5 Mn2 plus Fe3 plus and D6 that is Fe2 plus and CO3 plus cases. A vacant pair of d orbital results only by pairing of 3d electron, which leads to 1 and 0 unpaired electron respectively. The magnetic data agree with the maximum spin pairing in many cases, especially with coordination compound that containing of the ions. However, with species containing D4 and D5 ion, there are complication MnCn6 3 minus and has magnetic moment of 2 unpaired electron, while MnCl6 3 minus has paramagnetic momentum of 4 unpaired electron. FeCl6 3 minus has a magnetic momentum of single unpaired electron, while FeF6 3 minus has a paramagnetic moment of 5 unpaired electron, which is CuFe6 3 minus is a paramagnetic with 4 unpaired electron, while CuC2H4 3 whole thrice 3 minus is diamagnetic. This apparent anomaly is explained by Valence bond theory in terms of formations of inner orbital and outer orbitals coordination entity, which is MnCn6 3 minus and that is FeCN6 that 3 minus and COC2O4 3 minus are the inner orbital complexes involving the D2, that is D2sp3 hybridizations. The former two complexes are paramagnetic and later that diamagnetic. On the other hand, MnCN6 3 minus and FeF6 3 minus and CuF6 3 minus are the outer orbital complexes involving the sp3d2 hybridizations and are paramagnetic corresponding to 4 5 4 unpaired electrons here. We'll go ahead for the next. We'll talk about it, which is another about it here only, that is in terms of the questions that we have to cover up here. So we'll go ahead for the same. The question is, the spin only magnetic moment of MnBr4 2 minus is 5.9 bm. You have to predict the geometry of the complex ions here. Question is, the spin of only magnetic moment of MnBr4 2 minus is 5.9 bm. Predict the geometry of the complex ion. And this is the questions here, and that what we have to find out the answer for the same is that since the coordination number of Mn2 plus ion in the complex ion is 4, it will be either tetrahedral sp3 hybridization or square planar dsp2 hybridization. But the fact that the magnetic moment of the complex ion is 5.9 bm, it should be tetrahedral in shape rather than square planar because of the presence of 5 unpaired electron in the d orbital here. We'll talk about the another one, which is the another heading we can say that is about limitations of valence bond theory. Okay, so limitation of valence bond theory. In others that while the VV theory to a larger extent explains the formation structures, the magnetic behavior of coordination compound, it suffers from the following shortcomings. The first is it involves a numbers of assumptions. Second is it does not give quantitative interpretations of magnetic data. Third is it does not explain the color exhibited by the coordination compound. The fourth is it does not give you quantitative interpretations of thermodynamic or kinetic substitutes of the coordination compound. The fifth is it does not make exact prediction regarding the tetrahedral and the square planar structures of 4 coordinate complexes. The sixth and the last of the limitations of valence bond theory is it does not distinguish between a weak and a strong ligands as well. We'll talk about the another one, that has been the crystal field theory, which is CFT. Crystal field theory, which is CFT. In this, the crystal field theory CFT is an electrostatic model which considers the metal's ligand bond to be ionic, arising purely from electrostatic interactions between the metal ion and ligands. Ligands are treated as point charges in the cases of anions or dipoles. In case of neutral molecule, the 5d orbital in an isolated gaseous metal atom ion have a same energy, that is your degenerate, and this degeneracy is maintained if the spherically symmetrical field of negative charges surrounds the metal atom and ion. However, when this negative field is due to the ligands, either an ion or the negative end of dipolar molecule like NH3 and H2O in a complex, it becomes asymmetrical and a degeneracy of the d orbital is lifted. It results in splitting of the d orbitals. The pattern of splitting depends upon the natures of the crystal field. Let us explain splitting in different crystal fields here. So the first representing here is your, that is being your the crystal field, splitting it up in a octahedral coordination entity here. So for the first we have here is crystal field that we have. So crystal field splitting is octahedral coordination entities here that we have has been representing here. So in the same cases we have to go ahead for the same, and that here it is that in our octahedral coordination entity with the 6 ligands that surrounded by the metal atoms and ions, there are repulsions between the electron in the metal d orbital and the electron or negative charges that of the ligands. Such as repulsion is more, that is here it is that repulsion is more when the metal d orbital is directed towards the ligands, and then when it away from the ligand. Thus we have here is your dx2 minus y2 and dx2 that orbitals which points towards the axis along the directions of the ligands, that will experience more repulsions and will be raised in energy, and the that xy and dyz and dzyx, that is your xz, that orbital which are directed between the axes with a lowered in energy related to the average energy on spherical crystal field. Thus the degeneracy of the d orbital has been removed due to the ligands, electron metal and electron repulsion in the octahedral complexes to yield 3 orbitals of lower energy here. On the same cases, T2G that set and 2 orbitals of higher energy, which is of your EG set, and that the splitting of the degenerate levels due to the presence of ligands in the definite geometry is termed as crystal field splitting, and energy separations is denoted by delta O and delta N, and that the script of O is being octahedral representing. Thus, the energy of the two ER orbitals will increase by 3/5 of delta O, and that of the T2G will decrease by 2/5 delta O. The crystal field splitting, the delta O, or we have that depend upon the field that produced by the ligands and the charge on the metal's ions. Some ligands are able to produce strong fields, in which case and that the splitting will be large, whereas the other produces the weak field and the consequently results in the small splitting of d orbitals. In general, ligands that can be arranged in a series in the order of increasing field strength is given below here. That's what we will discuss about. So the d orbital splitting in octahedral crystal, that will be representing in the form of was in the form of like this only, is what yeah. So this is mean L L L and L here. So for that, its energy is increasing from down to upward. X Z Y. Coming towards it, this is energy, and that here it is. This is metal of d orbital, has been like this is here dx2 minus y2 dz2. Here it has been representing a line which is E of A 3 by 5th, which is your barycenter, and this has been representing T2G. Okay, this has been representing, this is dxy, dxz and dyz. Here for the same is your dx2 minus y2 dz2. This is your dxy, dxz and dyz. So this has been your average. This is free metal ion. Here it is your average energy of d orbital in spherical crystal field, and for this it is your splitting of d orbitals in octahedral crystal field here that we have. So this is all we have, d orbital splitting in an octahedral crystal field. For the same we have your representation in the form Br Cn minus Cl minus S2 minus F minus OH minus C2O4 3 minus 2 minus H2O, and then NCS minus Adita 4 minus NH3, and then En, Cn and CO. So here for the same that has been representing here. So such a series is termed as your spectrochemical series, where it is an experimental determined series that based on the adsorptions of light by complexes with different ligands, and let us assign electrons in the d orbitals of metals ions in an octahedral coordination entity, and obviously the single d electron that occupies the lower energy here, and that is T2G orbitals, and in D2 and D3 coordination entities that the d electrons occupy the T2G orbitals singly in accordance with the Hund's rule. For D4 ions, the two possible patterns of electron distribution arises. The first is the fourth electron that could either enter to T2G level and that pair with an existing electron, and that it could be avoid paying the price of the part and that pairing energy by occupying the EG of level. Which of these possibilities occurs, that depends on the relative magnetic of the crystal field splitting and delta of O and the pairing energy, where P represent the energy required for electron pairing in a single orbital, that the two options are, which is delta of O is less than P here, that the fourth electron enters one of the EG orbitals, that give the configuration of T power 3 to G and EG of T, that ligands for the which that delta O is less than P and are known as a weak field ligands and form high spin complexes, where if delta O is greater than P, it becomes more energetically favorable for the fourth electron to occupy 2Tg orbital with a configuration of T2G4 Eg0. The ligands which produces this effects are known as the strong field ligands and form low spin complexes here. Where in the same case for the calculation that shows the D4 and the D7 coordination entities are more stable for strong field as compared to the weak field cases here. For the same we'll discuss about it, which is the another way on the same, that is we'll talk about the crystal field splitting in a tetrahedral coordination entity here. So for the same we'll go ahead here for the same crystal field splitting in tetrahedral coordination entities. That what we have to discuss. In a tetrahedral coordination entity that forms the d orbital splitting inverted and is smaller as compared to the octahedral field that is splitting for the same metals and the same ligands and the metal ligands distances, it can shown that the delta 4 by 9 of delta naught that we have consequently in orbital splitting energies that are not sufficiently large for forcing a pure, and therefore low spin configurations are rarely observed here. Now we'll discuss about the another one that we have to discuss in terms of it, which is your the colors in coordination compound. But before starting with this, we have a diagram for this. dx2 minus x by 2 dz2 3 by 5th of delta t 2 by 5th of delta t here dxy dyz and dzy. This is tz. This is energy towards upward. This has been d orbital free ion, and here it is your average energy. That is, so we have your average energy of the d orbital spherical crystal field. This is your splitting of d orbital in tetrahedral crystal field that we have to talk about it. The orbital of splitting a tetrahedral crystal field that we have to discuss as well, and that is being important for two. Now here we'll be ending it up only, and that we'll discuss in the next coming class. That is being important as well, and we'll surely complete that in the next coming class soon. And before ending it up, it's a huge request from my side to all the viewers to please go through with the subscribe button, and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. Other than the chemistry, we are dealing with quantitative aptitude, where we had completed your we had started with arithmetical ability, and that is the second section is your data interpretation. In arithmetical ability, we had done your operations on numbers, LCM and SCF of numbers, decimal fractions, simplifications, square roots and cube roots, averages, problems on numbers, problems on ages, and then we start with discussing about surds and indices as well. After completing that, we had started with another topic that we have to discuss is your we had done your sociology and software engineering, and other than that we are dealing with the reasoning, where we had done your verbal reasoning, where we had done your gender mental ability and the logic reasoning. In non-verbal reasoning, we had done your series analogy classification, analytical reasoning, mirror image, water image, embedded figure, completions of incomplete pattern, figure matrix, paper folding, paper cutting, rule detection, grouping of identical figures, and then we'll discuss about the cubes and dies as well in the next coming class. In terms of chemistry, we are dealing with, we had completed your unit 1, where we had, that is the name of the unit is your solid state, where we had completed your general characteristics of solid state, amorphous and crystalline solid, classification of crystalline solid, crystal that is an unit cell, number of atoms in unit cell, closed pack structures, packing efficiency, calculation involving unit cell dimension, flame perfection in solid, electrical properties and magnetic properties. Unit 2 is your solution, where we had completed types of solution expressing the concentration of solution, solubility, vapor pressure of liquid and solution, ideal and non-ideal solution, colligative properties of determinations of molar masses, abnormal molar masses as well. In unit 3 is your electrochemistry, where we had to complete your electrochemical cells, galvanic cells, Nernst equation, conductance of electrolytic cells and electrolysis, batteries, fuel cells and corrosion. Unit 4 is your chemical kinetics, where we have to cover up the rate of the chemical reaction, factor influencing the rate of the reaction, integrated rate equation, pseudo-phosphorus reaction, temperature dependence of the rate of the reaction, collision theory of the chemical reaction. Unit 5 we have to cover up is your surface chemistry, is your adsorption, catalyst, collides, classification of collides, emergence, collide around us. Unit 6 is general principles and processes of isolations of element, which is we have to cover up the occurrence of metals, concentrations of ores, extractions of crude metal from the concentrated ore, thermodynamic principles of metallurgy, electrochemical principles of metallurgy, oxidation, reduction, refining, uses of aluminum, copper, zinc, and iron. Unit 7 we have to cover up. We had covered up that the P block element, where we had completed group 15 element, dinitrogen, ammonium, oxides of nitrogen, nitric acid, phosphorus, allotropic form, phosphine, phosphorus halides, oxoacids of phosphorus, group 16 element, dioxygen, simple oxides, ozone, sulfur, allotropic form, sulfur dioxide, oxoacids of sulfur, sulfuric acid, group 17 element, chlorine, hydrogen chloride, oxoacids of halogens, interhalogen compound, group 18 element. As well as in unit 8 we had covered up the D and F block element, where we had completed the positions in the periodic table, electronic configuration of D and block element, general properties of the transition element of the D block, some important compound of transition element, the lanthanoid, diactinoid, some application of D and F block element as well. In unit 9 unit that is the coordination compound, where we had completed the oneness theory of the coordination compound, definition of some important terms pertaining to the coordination compound, nomenclature of coordination compound, isomerism of the coordination compound, bonding in coordination compound, stability in the coordination compound, then importance and application of coordination compound. Well, that's what we have to discuss here. After that we'll have to cover up here. So it's a huge request from my side to all the viewers to please go through with the subscribe button, and please like, share and subscribe our channel, so that many and maximum people can get the information at once, and even you can also enjoy the video as well. Thank you. Hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion on the comment box. Thank you.